Hello everyone, this is section 7.3, hypothesis testing for the mean, sometimes referred to as small samples, but this is used when we do not know sigma and either the population is normally distributed or n is greater than or equal to 30. That's when we're going to use the t-distribution, as we saw with confidence intervals. And recall there is the little flow chart. That's your cheat sheet for the exam. The bottom tells you when to use Z or T, and basically T if we don't know sigma, as long as we're normally distributed or n is greater than or equal to 30. So we're going to use the critical value method, and that also is on your cheat sheet. So we have our 5-step process that we used in section 7.2 for the critical value method. So we'll follow that. And the only thing we need to really do before we get to the actual test is look at the guidelines for finding the critical values. So we find the level of significance, that's always going to be a given. Degrees of freedom are n-1, and then we're going to be using table 5. And in table 5, it's pretty self-explanatory. You just look at the row with the degrees of freedom, and if we have a left-tailed test, we use the one-tail column, and the critical value will be negative. So that's if it's left-tailed. If it's right-tailed, we're going to look at the one-tailed column, and the critical value will be positive. And then if two-tails, we look at the two-tailed column, and so it will be a positive and a negative for two critical values. So you can see how the table's constructed. We had used it for confidence intervals, but now we use it for the hypothesis test with one or two-tailed tests. So just intersect the degrees of freedom row with the appropriate column, and that's going to be our critical value. So a couple quick examples. I would always suggest drawing the distribution. So a t-distribution, you can assume almost looks normal. So just draw the distribution. And it's a left-tailed test. So therefore, somewhere to the left, okay, down the middle goes the t-score of 0. But somewhere to the left of that, shade in the tail, that's going to be t sub c, our critical value. We calculate the degrees of freedom, n-1, n is given to be 15 in this case. So 15 minus 1, which is 14. And then we're going to look under a one-tailed test because it's just left-tailed with a level of significance of 0.10 and degrees of freedom of 14. So the 14 row intersected with the 0.10 one-tailed will be our first column here. And so that would give us 1.345. But because it's a left-tailed test, we say t sub c is negative 1.345. So if you wanted to label it in the diagram as well. Okay, then we get a two-tailed test. Actually, let me move it over here. My sketch, that is. Okay, so there's my distribution. T equals 0 down the middle. Two tails. Shade in the tails. Those are the rejection regions when we use the critical value method. So there's two t sub c's, a positive and a negative. And we calculate, because it's two-tailed, and degrees of freedom, again, n-1. Kind of silly to write out the formula, but if you want to, you can. We get 23. Then we go to the table. Alpha is 0.05, but it's two-tailed. So in the table, under the two-tailed, 0.05 is the third column over, and we got a degrees of freedom of 23, so let's move down to the 23. It's the third column again, so it looks like 2.069. So T sub C would be, say, plus or minus 2.069. And on the diagram, if you wanted to label it 2.069 on the positive end and negative 2.069, to kind of squeeze it in there on the negative t-square. Okay, so then the t-test for the mean is basically the same as the z-score formula. This is on our formula sheet. And on the formula sheet as well, it does gives the formula, and it does state the criteria. When we don't know sigma, sample's pretty much always random, but then we have to be told either the population's normally distributed or n is greater than or equal to 30, and there's the formula for degrees of freedom. But notice that the t-score, test statistic, is essentially the same as the z, except instead of sigma, we have s, okay? Because we do not know the population standard deviation sigma, we know the sample standard deviation s. So there's our formula, and it's a given, and we're used to the calculations with that. There's our 5-step hypothesis testing procedure, which is again the on your cheat sheet as well. And so we'll get to some examples. Okay, so here we're investigating the effect of insecticides on table wines. 25 bottles of wine are sampled. Let's write out the given. That means N is 25. And they determine the amount of lead. Sample mean was 0.409 ppm, stands for parts per million. So that's the sample mean, so that's X bar, 0.409. And the sample standard deviation. Okay, so it's that sample mean literally, and it literally says sample standard deviation. So remember, sample standard deviation is S, and that's 0.051. So make sure you understand, once again, we've drawn this many times, but if we're talking about a population versus a sample, and the notation for mean and standard deviation, for the mean of a population, it's mu. For the mean of a sample, X bar. For the standard deviation of a population, sigma. And for the standard deviation of a sample, S. Okay, so then continuing based on the data, the mean lead content in the wine, is the mean lead content in the wine significantly less than 0.42? And assume the variables normally distributed. Now that's a piece of information that we need because the sample size is less than 30. So a lot of times that's why we call this small samples, because this is characteristically what happens when you do a real test in the hypothesis test in the real world. You're not going to be able to do very many more than 30. So again, the flow chart if you like. But see, the point is we don't know sigma, so fortunately it's normally distributed, and so therefore we're going to use T. So this information tells us to use the T distribution. Okay, and let's see, alpha's 5%. significance, change it to 0.05. Now, we'll start by first going through the 5-step procedure. First step, HO, identify the hypotheses, or state the hypotheses, identify the claim. Okay, so it has to do with this piece of information, less than. The less than symbol is going to go with HA because there's no equality. So, and that's the mean amount of lead that we're talking about. So mu is less than 0.42 is our claim. And that would be HO is the complement, mu is greater than 0.42. Alright, the second step is to find the critical value. So we're going to draw a distribution. And note that because the inequality in the alternative hypothesis is less than, that it's a left-tailed test. Okay, I'll restate the fact that alpha is 0.05. Okay, let me draw the left tail. That's T sub C. Shade in the rejection region, which is in the tail. We need the degrees of freedom, which is n minus 1, or 25 minus 1, so 24. Okay, so then we go to table 5, and T sub C is, looking at table 5 here. Okay, it's a left-tailed test, so it's one-tailed. Degrees of freedom of 24, alpha 0.05. Okay, so one-tailed 0.05, our second column. Degrees of freedom of 24. Looks like 1.711. But it's a left-tailed test, so therefore T sub C is negative 1.711. We can put that in our diagram. Alright, so then our third step is to calculate the standardized test statistic T, which is x bar minus mu over S divided by the square root of n. And so substituting, get 0.409 minus, okay, mu is always the hypothesized population mean of 0.42 in this case, all over S was 0.051 divided by the square root of n was 25. Alright, so calculating that, we get negative 1.078, and then we make our decision. And negative 1.078, if you want to place it in the table, or in your sketch, that is, somewhere between 0 and negative 1.711. Point is, it's in the non-rejection region, so therefore our decision is to fail to reject HO. So remember, it's always with respect to HO. If it's in the rejection region, reject HO. If it's in the non-rejection, as we have here, fail to reject HO. And then we could form our conclusion. All right, if I'm failing to reject HO, it basically means that HA is really not, we can't have confidence in HA. So that's the claim. So therefore, and remember, we use the word support in our answer when the claim is HA. And so therefore, there is not enough evidence support the claim. And again, you could use your little table, our cheat sheet once again. That table's on the side here. Claim was HA, so our second column, we're failing to reject. So the conclusion, there's not enough evidence to support the claim. Okay. All right, so another example. From past experiences, this realtor believes the average score on a real estate exam is 75. So that's his hypothesis, and is means equals. So right away, if you want, you could actually state the hypotheses, HO and HA, and identify the claim. Okay, now it's equality, so that goes with the null. So mu is equal to 75 is the claim. And therefore, the complement, mu is not equal to 75, is the alternative. All right, let's read out and write down the given. Took a sample of 20 students. And on that sample of 20 students, the mean was 71, so that's the mean of the sample, x bar. And the standard deviation was 6.6. And realize that's in the same sentence regarding the 20 students, the sample, so therefore that's the sample standard is 6.6. And test the realtor's claim that the average score is 75. We already set up the hypotheses, and we're told they're normally distributed, which is a piece of information that we need again. And if we look at our table, our flow chart, we don't know sigma. N is not greater than 30, but it is normally distributed. So therefore, T distribution. Okay, and the level of significance this time is 1%, or 0.01. Okay, so we already did the first step, stated the hypotheses, identified the claim. Second step, critical value. But now we have a two-tailed test because the inequality in HA is not equal to. So it's a two-tailed test. I'll reiterate that alpha is 0.01. Our degrees of freedom are 20 minus 1, or 19. So we want our critical values. Okay, but you can put the t equaling 0 down the middle. You got two tails this time, and the rejection regions are the two tails. So we've got a positive t sub c here, and a negative t sub c here. And that T sub C from table 5. At this point, you should be comfortable using it. I'll show it one more time. 0.01, two tails. So go to two tails, 0.01. That's our final column here. Degrees of freedom were 19, so just move down to the 19 row. Looks like 2.861. So therefore, T sub C, because it's two-tailed, we'll say plus or minus 2.861. So if you wanted to label the diagram, 2.861 on the right and negative 2.861 on the left, separating the rejection from the non-rejection. Okay, then we calculate our standardized test statistic. And again, it's x bar minus mu over s divided by the square root of n. And x bar is 71 minus mu. Again, mu is always the hypothesized population. Mean, in this case 75, divided by s is 6.6 over the square root of n was 20. So we crunch that down, we get negative 2.710. And then our decision, okay, go to the chart, negative 2.710. It's pretty close. If alpha was different, we might actually reject HO, but negative 2.710 is in the non-rejection region. So therefore we failed to reject HO. Okay, and then our conclusion. So since HO is the claim and we're failing to reject it, and since HO is the claim, we use the word reject in our answer, so there's not enough evidence to reject the claim. You could use the table if you like. Okay, so a final example, and in this example, this is a classic, where we're just given about some data. We have a little note at the top, though, about the p-value method. That's actually optional, so we're not going to study that, so we'll just use the critical value method for the t-distribution. But here's a classic example where we're given some data. So university claims the mean class size for full-time faculty is fewer than 34 students. So fewer than means strictly less than. And to test the claim, we select 12 classes. So in the given information, sample size is 12. And here's actually the 12 class sizes. And the results are listed below as it says. Okay, so when you're given just the raw data, you want to use technology, the statistical features on your calculator for X bar, the sample mean, and S, the sample standard deviation. So depending on what calculator you have, I have we've shown this before, but I have this TI-30, and if you have that one, then you could follow the keystrokes here. If you have a different one, then just simply Google or email me and I'll Google for you, and you'll find a video on how to calculate the desired statistics for your sample data. All right, if I clear everything, it looks like I'm already in stat mode. If I take out the, but I'm going to stat, one variable, enter. I want to list my data. Okay, we've got some old data in there, so I should clear it, but I'll just clear it as I go. So 35, frequency 1, 28, I'll just override these. Frequency 21, 29, frequency 1, 33, 32, 40, 26, 29, 36, 33, 30, and 28. Okay, so that's my data. Now I just go to stat var, calculate, oops, stat variable, and there's get the calculations. Toggle over, there's X bar 31.583. And our standard deviation, we use S, sample 4.033. And we should assume, okay, because this would be a problem otherwise. I guess it's not mentioned in the problem. Oh, yep, it is, thank goodness. Assume the variable's normally distributed. Okay, because we need that when n is not greater than or equal to 30. But this tells us to use the t-distribution because we don't know the population standard deviation sigma. Alright, so then from here it's the same routine as the previous problems, but again, when you have the raw data, use technology. You don't have to do that by hand. So alpha's 0.1 here, 0.10. Alright, so let's go through the process. First step, hypotheses, HO, HA, identify the claim. It was fewer than 34 students, less than goes with HA. So mu is less than 34 is our claim. That means mu is greater than or equal to 34 is the null. Second step, critical value. Draw the distribution. Note that the inequality symbol in HA is less than. So therefore it's a left tail test. Alpha is 0.10. Degrees of freedom. There were 12 pieces of data. 12 minus 1 is 11. And T sub C. Okay, we've got T equaling 0 down the middle again. You don't need to write that, but T sub C, because it's a left-tailed test, is on the left. There's the critical region then in that tail. And I'll trust that you could look that up in the table. You get 1.363, but it's left-tailed, so negative. 1.363. Okay, so then our standardized test statistic. Again, the formula x bar minus mu over s divided by the square root of n. And x bar was the 31.583 minus mu, again the hypothesized population mean, in this case 34, over s, the 4.033 divided by the square root of n, which was 12. And so that gives us a standardized test statistic of minus 2.076. And then in the diagram, minus 2.076 doesn't have to be to scale or anything, but that falls way over here, right? In the rejection region. So therefore our decision is to reject HO, and then our conclusion. And use our little table if you like, but I'll just argue this intuitively. For rejecting HO, if HO is the claim, the word support is in the answer. And then if we're rejecting HO, that means the claim is good, so there is enough evidence to support the claim. Okay, so that's the end of section 7.3. So we'll see you ready for 7.4.